And Professor Narayan Malakar, are you able to unmute yourself? Professor Narayan Malakar, can you unmute yourself and just give a quick introduction?
Hello.
Hello.
Yes,
Just
good morning. This is Priya.
yeah.
Presently, I'm a research scholar in Anna University, Chennai.
Okay.
Yeah.
Okay, good.
I'm doing my research in the area of economic load dispatch. So this is brief about me, and I'm having a 10 years of experience in teaching an industry.
Okay. Okay,
Yeah.
good.
Thank you, sir. Thank you.
Thank you. So we'll start at 10:10, I guess. Suppose whosoever has to join would join by that point of time. Roshan, I hope the slides are visible.
Yes, sir, it's visible.
Okay, good. So moving beyond what has been taught over the course over the last few days during this faculty development program, we will be touching upon few innovative topics which could be of interest to one or more of you, possibly in your research and otherwise also. One of the topics we'll be running the session from 10 to 1 o'clock, 3 hours. And I'll be happy if you if you wish to ask questions anywhere in between. I'll prefer that rather than answering only at the end of the session. So I'll request the organizers to unmute all the participants as and when they join. We'll be happy to take up questions as and when you feel like, and feel free to ask anything. One of the areas that we are touching today is on demand side management. This is a challenge that the industry, the utilities have been, the power utilities have been focusing upon over the last, I would say, 50 years. The topics of demand response, demand side management, they started coming up somewhere in 1970s, not in 60s, but in 70s, they started picking up. However, over the last 50 years, there has been little traction on how to create demand side management. Essentially, for the reason that real-time demand, obviously the challenges of demand, the challenge of demand and supply balance in a grid are challenges that are to be handled in a real-time situation. So to handle those real-time challenges, you need to have solutions which provide you real-time information. And to do that, you need to have monitoring of the demand in a real-time fashion. Traditionally, all our meters on the demand side for all type of customers used to give us energy consumption over a period of 1 month cycle or 2 month cycle, thereby not having the provision of providing real-time response into the system. In such a scenario, it was difficult to create any demand side management solution for the utilities, and they were not able to respond to any requirements of demand management as such. Anybody has any thoughts on what demand side management is? any idea on what demand side management is? Any participant? No. Okay. We
Uh, Good morning,
yeah,
sir. Sir,
yeah,
Dr. Nishant here.
yeah, please.
Sir, I have studied few papers of a professor was there. He died last year in IIT Roorkee. He has made the demand side response, making some changes in loads. Like we say that we have to cut the peak and we have to fill the valley. In that case, load shifting we have done in the demand side management.
Hmm. You are correct. I think somebody has to mute. Somebody, okay. Yes, true to a certain extent, load filling and those concepts are there. However, the issue that I just wanted to stress upon was that demand side management has not really picked up in the industry as such. Theoretically, there has been a lot of papers, a lot of research that has gone into how to create demand side management. But unfortunately, from a practical industry perspective, it was not many utilities were able to create any demand side management mechanisms, which would either in real time or in a longer term frame, the utilities were not able to do it. In this session, we'll try and understand what are the issues that are to be handled in real time, what are the issues that are to be handled in a longer term time frame from a practical industry perspective, going beyond what is the theoretical perspective. So as I take you through this journey, you will possibly be able to appreciate. We just start from what are the numbers in the Indian power sector as of now. So on the right hand side, if you see right hand side of this slide, if you see the sales mix of the customer side, 27% of the energy consumption is being done by the domestic consumers, 7% by commercial, 5% by industrial low voltage, 36% by industrial high voltage, 18% by agriculture and some others. So one of the key questions that we need to answer and understand is who has the potential to provide demand side management. Traditionally, the potential was focused on the industrial high voltage consumers or the industrial low voltage consumers, which constituted a significant demand portfolio. And industries would typically put up a meter, time of day meter on their side to manage their demand during times when the system demand was at its peak and when the supply was not sufficiently available. This was what was being practiced even till date. This is what essentially is being practiced on for a real-time demand side management. However, with the advent of smart meters, the potential of other segments of the customer side, like domestic, commercial, and agriculture, also comes into picture, wherein they can also their demand would be monitored on a real-time basis, and real-time demand side management, real-time demand responses can be provided by those consumers. So that is where the rollout of smart meters across the country would bring in more opportunities, and that is why the focus of this session is on demand side management. There are other facets apart from smart meters, but this is one of the facets. In a longer term time frame also, from other perspective also, having an understanding of what is the portfolio of energy sales across the country helps us to understand which segments are to be targeted and with what strategies. If domestic consumers have to be targeted with certain strategies, what would be the strategies for domestic consumers? What would be the strategies for industrial consumers, and so on and so forth, and for that matter, for agricultural consumers? If you see vis-a-vis on the other side, the peak demand versus the peak met demand and the deficit in the system, that also is reflected. This is slightly dated, about 2 years old. We have updated numbers in the market as of now, but this just does give us an understanding of what are the system numbers as of now. What is happening in the world is the pattern of demand is evolving. The pattern of demand is evolving from purely traditional perspectives of residential, industrial, and agriculture demand portfolios. Our more and more energy requirement is being driven by electric demand. Our vehicles are now being driven by electricity. They are using batteries. In our kitchens also, we are using more and more kettle, more and more devices, ovens, etc., which are dependent upon electric supply. Our heating in our houses, geysers, we are using more and more geysers, electric driven geysers. Same way, air conditioning demand is also increasing, and so on and so forth. The way by which we are using electricity as a form of energy, that is increasing in our lifestyles, and the overall consumption of other energy vectors like oil and gas would significantly reduce over a period of time. This is essentially focusing on more and more decarbonization of the energy supply systems. That is one of the change that is happening in the system. Another change that is happening in the system is more and more smart grids, more and more interconnections between the system, smart digitization of the system, IoT, bringing in IoT into the systems and bringing in smart meters. These are components, these are changes that are happening to interconnect the system, interconnect the points, interconnect the nodes, interconnect the consumers from the system and different components in the system. So that visibility in the system is more. The system operator is able to see what is happening in the demand on different nodes, and at the same point of time, the consumer is able to see what is his real-time consumption. And accordingly, if he's asked to respond to those the supply patterns, he can possibly respond. But all that is getting through significant communication getting embedded into the system, grids becoming smarter, and digitization of the grid happening at a fast scale. This is another change that is happening. Yet another change that is happening in the grid is more and more distributed form of generation that is coming up in the system. That is coming up in the form of renewable energy, in form of rooftops, in form of wind turbines, and so on, in form of battery storages. There, if not generation, at least storage facilities are coming up. So the traditional way by which we used to generate electricity by way of large power plants, that is going away. That is shifting towards a scenario where more and more generation is happening through distributed generation in the form of renewables and in other forms as well. So this and renewables, unfortunately, are uncontrollable mechanisms of generation. This leads us to a situation where rather than having large controlled power plants, we have to handle a system in which there are large number of generating stations which are essentially uncontrollable and distributed into the system at various voltage levels and at lower voltage levels of 230 volts as well. Our specific examples are that of rooftop solar. Another change that is happening in the system is on the component side, where the components that we are using, like the fans, the air conditioners, the geysers, they are becoming more and more efficient. If you have heard of Bureau of Energy Efficiency, you can very well appreciate that star rating of all electric appliances is evolving over a period of time. This essentially rates the devices based upon their energy efficiency. So while we have got star rated air conditioners, now we also have got star rated, 5-star rated, 3-star rated fans, washing machines, and so on and so forth. So as we start using more and more devices in our ecosystem, their standardization in terms of energy efficiency would also become more and more prevalent. So that is important because the quantum of energy that we are consuming right now and which we plan to consume is significant. And in order to meet that, you need to ensure that the energy consumption is done in an efficient way. If we start consuming electricity or energy in an inefficient way, obviously our requirements would continue to increase, despite that the fruitful outcome from that energy consumption is low. Specifically, this type of energy efficiency focus is more on those parts, more on those part of the industry where energy consumption is happening on a very large scale. Typically, industries now, data centers, buildings, malls, all these infrastructure which essentially use significant quantum of power at the same point of time. They have started focusing on making the system, making the components more and more efficient. So these are the four facets of energy supply systems that are happening in the grid. That is, one is making it more electric, the second one is making it more interconnected, third one is making it more distributed in a sense, and fourth one making it more efficient in a sense. This is what essentially touches the demand response and the this is what touches the basically the demand profiles in the system over different time scales and even in the longer time frame as well. Another change that is happening in the grid is the nature of the generation, nature of the generation shifting from large power plants to smaller RE-generated based power plants. If you see this graph and if you see this figure and you can make out that on the left hand side, we used to, the conventional generation system was that on the left hand side, we had got controlled and dispatchable supply systems. That was the conventional system in which our generation was significantly dependent upon large power plants whose generation was controllable. We could control and dispatch them based upon what the requirement on the demand side was. So if the demand would vary, and obviously the demand was an uncontrollable parameter, though it was predictable, but it was non-controllable. So you could predict, you could forecast it, but you could not control the demand. So we had a scenario conventionally in which the demand was non-controllable, but the generation was significantly controllable. We are slowly shifting towards a system in which we are focusing on bringing in demand side management. However, on the generation side itself, the things have started evolving by this RE penetration, which is essentially less controllable vis-a-vis the traditional conventional power plants. However, on the customer side, the components now are becoming, to an extent, are becoming controllable in terms of when do you charge your electric vehicles. That can be controlled, if not directly by the grid operator, possibly by the customer. And he's able to see his demand patterns as well. There are, apart from that also, there are various ways, flexible resources we can create in the system, which can essentially, like the talk about green hydrogen that we talk about, essentially talks about converting the excess solar generation into green hydrogen. That is one way of managing the excess generation at times when we are not able to consume it. So this is how you try to manage the demand and supply imbalance by somehow managing the demand either creating new demands by way of consumption patterns or shifting of the demand at different points of time, creating energy storage on the customer side, like electric vehicles. So, essentially bringing in demand side flexibility in the system. These are the two changes that are happening in the grid, and these are the things that we possibly will focus upon. Why we need to focus on demand side management? The challenge is that even if you take the case of example of Indian power grid, we have an installed capacity of about 500 gigawatts. However, the peak demand in the system is somewhere around 250 gigawatts. So we have installed significantly high capacities, despite that we are barely able to fulfill the peak demand in the system. This creates challenges of system outages, and this is we need more and more reliable power supply rather than only having installed capacities which are not able to supply power as and when required. Essentially, the grid in itself, because it is made up of various components like generation, transmission, and all generators are not available at all points of time. Networks may fail at some point of time. There may be congestion in the system. There may be network failure in the system. That can lead to significant demand supply imbalances in the system, even during when the demand increases, maybe during festivals or during hot summers when the air conditioning demand increases. The requirement of peak system generation increases like anything. Unfortunately, the system does not have the capacity to fulfill the demand at those point of time, either due to generation non-availability of peak demand, peak generation, or possibly due to transmission system constraints. This short-term peak management has always been a challenge for the DISCOMs. So distribution companies have always faced this challenge of how to manage this demand when such events occur where sufficient generation is not available and system has got transmission network system has got constraints. So presently in this session, we'll be focusing upon demand side management as a solution to help manage these issues and to help the growing integration of renewables into the system. I'll be happy to take up questions, if any, at this point of time. Anybody has got any questions?
Real-time supply and demand balance is made through power balance equation in economic load dispatch. How demand side management will come into picture in terms of generation schedule?
How demand side management will come into picture in case of generation schedules?
Scheduling, yes.
Scheduling. Presently, when you are doing your generation scheduling, you are considering that the demand is, you have a certain demand forecast in mind. This is how you do it?
Yes, yes, sir.
Yeah, when you have got a certain demand forecast in your mind, you essentially, based upon the forecasted demand, you try to switch on the generators which with incremental cost. So first we try to operate the cheapest possible generator, then the next costlier, next costlier, next costlier, and so on. During periods of highest demand, we have to start operating the costliest generator in the system. This is how we do it. However, even while we are able to run the costliest power plant in the system, it may be possible that we may not be able to fulfill the demand at that point of time. So essentially, what do you do at that point of time? You answered that question. What would you do?
Sir, load curtailment or
Exactly. Load
peak
curtailment
saving
is one.
should be.
Yes. Other than that?
Peak shaving is there.
Peak shaving, how do you do that peak shaving? Through some demand side management mechanism. Load curtailment is not a happy thing for the electricity
Consumers.
suppliers and neither for the consumers, obviously. No, not for happy, not a good scenario for either of those. So rather than going in for load shedding, essentially what we should aim at is we should try and create a mechanism by which, rather than trying to start the costliest generator in the system, we should try and minimize the demand at that point of time and try to shift the demand which exists in the system, try to shift that demand from peak hours to non-peak hours, such that we are not forced to run those power plants, the costliest power plants, and also not to go in for load shedding. That is what is the possible scenario, in which case essentially we try to manage the demand, we try to manage the demand in such a way such that the peak demand is shifted from those scenarios to other scenarios, and thereafter, based upon the quantum of demand side management that we can bring in, we revise our forecasted demand and we do a scheduling based upon the revised demand in the system. Does that sound okay?
Yes, sir.
Does that
Sir,
answer?
certain
Yeah, please.
certain contingency cannot be avoided. Can demand side management able to handle those contingencies?
Yes, demand side management can help to manage those contingencies as well. Not an issue. It can.
Yes, sir.
Obviously, as we go through this session, you will realize that not only does the demand side management, not only are we able to handle long term. Look, when we talk about power system, we always have long term perspectives as well as medium term time frame perspectives as well as short term perspectives. So when we are talking about demand side management, obviously we'll be able to take up, I'm not saying obviously, but yes, we would be able to take up the perspectives on a longer term time frame, on a medium term time frame, and from a shorter term time frame as well. So whether it is long term energy system planning or electricity system planning, or a medium term time frame in few years, or short term time frame of few minutes or few hours or few seconds also, that also can be handled by demand side management mechanisms. We can do that. We'll see how we do it.
Yes, sir. Thank you, sir.
As far as the definition is concerned, you can Google it out. There are a variety of definitions available in the system. One of those is it is a portfolio of measures to improve the energy system at the side of consumption. It also talks about, if you see the Forum of Regulators definition, the action of distribution licenses beyond the customer meter and with the objective of altering the end use of the electricity, whether to increase, decrease, or shift the demand, and so on and so forth. So even if they have to manage the intermittent load demand, that is how it would run. So overall, whatever demand side changes we are able to enforce, load shedding obviously is the last one of those. Whatever demand side changes we are able to enforce in order to align the demand with the available generation, we'll be focusing upon those. One of the facts that we need to differentiate here is that presently, when we use the term demand side management, we are not focusing on the supply side management perspectives. In this case, when we are focusing on the supply side, we have got the thermal power plants, we have got the high voltage transmission systems. In all these cases, any management happening on the supply side does not constitute a part of the demand side management. Demand side management would essentially comprise of actions being taken on the demand side, like curtailing the usage hours, usage of efficient devices, using of solar devices, shiftable loads, and so on and so forth. On the demand side, on the lower voltage side, distribution loss control, load shedding, use of renewable energy, etc. These do not constitute a part of the demand side management. First, to understand the demand side philosophies, what we need to classify the demand or classify the demand side management, depending upon how do we classify the demand. Similarly, we also classify the demand side management strategies as well. One of the ways is through energy efficiency. It is a way of expressing the energy performance of an energy consuming device. So by improving the energy efficiency of a system, we can make, by improving the energy efficiency of a system, we can make a change in the system's, in the overall system demand. It essentially, by improving the efficiency of the component, it essentially helps us to reduce the overall demand in the system from an overall load curve perspective. So if you're using a efficient bulb, if you're using an efficient fan, or if you're using an efficient air conditioner, obviously it leads to a permanent reduction in the consumption across the load curve. It provides same or better energy services, but the overall energy consumption that happens in the system, that is improved. Demand response as such, this energy efficiency is one part. Demand response as such, it leads to reduction of overall system peak load as end users who shift their operation of some of their loads from peak hours to off-peak hours. So two facets that we see here, one is energy efficiency, another one is demand response. These are two different things. They both constitute a part of demand side management. So energy efficiency on one side permanently reduces the consumption on all time scales, whereas demand response shifts or reduces the overall system peak load rather than shifting the complete demand. Majority of the demand response programs are designed to enhance reliability of the system and to reduce energy production from fossil fuel-based power plants. This has been the conventional focus of the system. As you indicated, yes, there are a variety of demand side management strategies. Demand side management strategies in case of energy consumption, conservation, that is one facet in which the demand on all time scales, whether it is during peak hours or off peak hours, at all time scales it reduces, because if you're using an energy efficient device, obviously energy consumption at all times of scale would reduce. Impact on the peak demand, it will reduce. Impact on the overall energy demand, that will also reduce. Peak clipping is another strategy in which we clip the demand at the peak load periods. Load, essentially to bring in load leveling. It reduces the peak demand. It also reduces the overall energy demand. Load shifting is yet another strategy in which we shift the load from peak hours to off-peak hours. It reduces the peak demand, but does not make any change on the energy demand. Flexible reliability, it induces change in the load as per supply, such that the peak demand decreases, the energy demand may reduce, it may not reduce. Strategic load growth during hours when we want to increase the demand, promoting appliances requiring electricity vehicles during those hours when the system generation is not available. So peak demand may increase, the energy demand would definitely increase. Valley filling is another way in which we increase the demand during hours when the system demand is low, so that the peak demand does not change, but the energy demand changes. Valley filling is done, one of the reasons why valley filling is done, because of the availability of system generation, wherein we are unable to switch off the generating power plants because of one or more technical reasons. At that point of time, we would prefer to have an additional demand in the system rather than being forced to reduce the generation available in the system. I hope these are the strategies that one of the participant has indicated.
Yes, sir.
Okay, okay. Uh, there are beyond those classification, we also need to have beyond those classification, we also need to have an understanding of the demand side service management from time perspective. On time scales, how do these things vary? So if we are using energy efficiency mechanisms and behavioral changes in the system, the impact it would have on the load curve would be in a longer term time frame. That means if it happens, it will continue to impact on for years together. There could be some demand response management strategies which would help. So if the shape is being changed, it changes in the consumer behavior and the impact is on a longer term time frame. Shifting the load is obviously a shorter term demand response management strategy in which we mitigate the RAM, capture the surplus renewables. Essentially, we try to shift the demand without any net reduction in energy consumption of the system. Load shedding again happens in a similar time frame of days to hours, in which we shed the resources in terms of aggregated potential to reduce the demand at the times of peak demand or system emergency through individual load curtailment by end consumers. So whenever such contingencies occur, we go in for load shedding, and load shedding is not done in years period. It is done for few hours or maybe maximum days. Load shedding is usually for a couple of hours, not more than that. Another facet, another time frame that we need to focus upon is in a very short term time frame, and those actions are called as demand shimming. Demand response linked to flexibility, that the ability of the load to dynamically adjust the demand. So as the system supply becomes less available, the mechanism, the technical solution is to for the load to be changed depending upon how much demand is load to be changed depending upon what is the demand supply imbalance in the system. This essentially are mechanisms to provide fast demand response in time frames of few minutes to few seconds. Components of demand response, how do we go about creating a mechanism of demand response? The components involve identifying the stakeholders involved in providing the demand response. Three broad divisions that we identify that needs to be focused upon is the utilities, the load aggregators, and the consumers. These are the three big players in demand response management scenarios. Demand response programs, they require a certain level of technical readiness from the perspective of each of the stakeholders. So when we are designing such demand response management programs, utilities have to be handled in a separate way. Load aggregators, those entities which aggregate the load, they have different strategies have to be adopted for those. And customers, obviously, there will be different strategies for them as well. But we need to segregate these and understand how these have to be modeled. Technology obviously would enable, and the type of technologies that would require is hardware in terms of communication infrastructure, software in terms of algorithm, and so on. Hardware also in terms of maybe the optical fiber cables, communication information, communication hardware that would be required in the system to transfer the information from different nodes to the system side. Technological perspective for smooth conduct of residential demand program. That means what technology can be adopted to implement to get the residential demand response program in line with the system supply available. So all these facets have to be categorized and understood to make any successful demand response program. The stakeholders, as I just discussed, there are stakeholders. Utility is one of the key stakeholders, obviously because its demand is to be managed. Load aggregator is an entity which combines the demand from different loads and tries to aggregate them to provide appropriate demand response to the utility. Consumers, those consumers which are willing to participate in the demand response program, and maybe through some economic or non-economic signal. And regulator is one of the stakeholders which provides appropriate regulatory framework for providing demand response in the system. So the rules and regulations for providing demand response are set by the regulator as such. Who all are the entities which can provide demand response? So some of the identified entities which have got a strong potential to provide demand response are residential demand response candidates, commercial demand response candidates, and industrial demand response candidates. I'll just take a quick sound break till the time you go through this slide. I'll just give. Apologies for the quick break, a short break. So candidates for demand response, these are the candidates that we see here. Any questions up till now, whatever we have discussed? Any quick questions? Now we have sufficient number of participants. Any participant having any question, he can unmute himself, herself, and ask a question. So these are the typical candidates that are there for providing demand response. Residential demand response candidates, obviously, high voltage, the HVAC systems, lighting, refrigeration, washing machine, clothes dryers, hot water heating, all these controllable appliances which can form a part of residential demand response programs. Similarly, from the commercial demand response side, similar type of components, similar type of devices which can provide demand response. On the industrial scale, again, HVAC, cold storage, lighting, backup generators, and so on. These are some of the components that can be that can vary their demand, that can whose consumption patterns, whose consumption timeframes can be changed to vary the demand in the system. Type of demand response programs, you would have heard of some or more of those. We have got the price-based demand response programs, which are real-time pricing, time of use, critical peak pricing, incentive-based programs, direct load control, emergency demand response programs. So when the question asks whether we can provide it for short-term time scale on and very short-term time scale, yes, we can devise such programs. All these programs on this first two blocks, they are voluntary programs, incentive-based programs, which are mandatory. You've got capacity markets, you've got interruptible curtailable services system, market-based programs like demand bidding, demand buyback, or ancillary service market. So there are a variety of such demand response programs that have been conceptualized in the literature. And obviously, depending upon what market framework we are working in, which country we are working in, we could adopt one or more of this to shape up the demand, to vary the demand in the system. So this gives a comprehensive understanding of what type of demand response programs, their characteristics, their pricing mechanisms, they would vary depending upon their types. And also, some of them are voluntary. The customers can participate on their own with their own interest, with financial interest, or some of them can be made mandatory. And otherwise, some of them can also be market-based programs in which you have an appropriate market structure to provide those demand response mechanisms. In case of price-based demand response programs, customers essentially respond to some price signal. They adjust their demand based upon certain price signals, and this essentially results in a change in the energy consumption pattern. So we use price signals to influence the consumer behavior, promoting either energy efficiency or promoting shifting of demand. Some of the examples in price-based demand response are real-time pricing, time of use pricing, critical peak pricing. I'm not going into the definitions of each one, but you can understand from the nomenclature itself that these, based upon these, customers may respond to different price signals voluntarily and provide demand response. Time of use pricing mechanisms in which customers, based upon what are the tariff at different time periods in the day, it would vary, and customers would change their energy consumption accordingly. They'll reduce their demand during hours of peak pricing, higher pricing, and during periods of lower prices, they would tend to consume more. This is to ensure that we shift the demand from high demand period or high price period to low demand and low price periods. Critical peak pricing mechanisms to primarily focusing on short-term time frame when there is shortage for a very short period of time, emergency periods. The charges can be very high during emergency periods so that people shift their demand from those periods to other periods, or they may voluntarily offer their demand response during those times. Similarly, real-time pricing, in which the prices are dynamic in a nature and they vary depending upon the demand-supply balance at all points of time. And consumers may respond to those signals at various times. On the other side, incentive-based programs, can be designed in terms of rebates, in terms of if they are making some direct payment or some credits, if you want to offer some non-financial incentives in terms of points and rewards or recognition, these can also be brought in the system. So financial as well as non-financial recognition, rewards, incentives can be designed so that customers participate and respond, change their demand accordingly. Voluntary programs would involve direct load control, in which the consumers agree for the utility to control some or more of their household devices or commercial devices. So essentially, it allows the utility to control the demand of some of the high power consuming systems in your household. Similarly, emergency demand response program could be voluntary programs in which there are incentives for the customers who participate in load shedding during contingency events. Capacity markets, on the other side, are market-based programs in which customers oblige themselves to provide a certain level of load shedding whenever there is a contingency, whenever there's such a price signal available, whenever there is a requirement. So essentially, we do run capacity markets in some countries, in which either on the generation side or consumers also form a part of the capacity market, in which they can provide that level of load shedding to the market by offering that load shedding during periods of contingencies. Interruptible curtailable load services, in which it is a compulsory program in which customers join to adjust or shed their load based upon some discounts or fair prices being offered by the utilities. Demand bidding, demand buyback, these are commercial approaches to balance the demand and energy supply. Ancillary services market, on the other hand, it is a market mechanism, a large market mechanism in which large consumers can provide ancillary services apart from the actual power P being supplied. So they can supply all sort of ancillary services like ramping, like reactive power, black start facilities. So all those services, demand response also forms a part of those services. These can help to reduce the load, and the customers would benefit from in terms of some incentive, in terms of remuneration from participating in the market. This is a broader classification of the things of the demand response mechanisms. As far as demand response automation is concerned, how do we do it? How do we create it? It could either be manual responses, that is, a person responds to a certain situation, and all the communication would typically be manual. It could be phone calls, emails, or other form of direct communication. It could also be, automation could also be automatic, in which it can be done through smart devices, sensors, etc. It could be load shedding actions that are triggered automatically based on criteria, certain price criteria or frequency criteria. Frequency criteria, you see, there has been mechanisms in the Indian grid as well, in which the prices of overdrawing are dependent upon what is the frequency at that point of time. There could be semi-automatic demand response mechanisms, in which there could be some predefined functions as well. So variety of communication mechanisms, automation mechanisms can exist in the system depending upon the technology available. Any questions up till now? Anyone has got any questions? Yeah.
Sir, like demand side management, supply side management techniques should be available to. Is there any technique like supply side management also available for load changes, to mitigate load changes?
Essentially, power system was always designed
Yes, sir.
It was always designed in such a way that supply would follow the demand. So as
Yes, sir.
such, all mechanisms like you load, economic load dispatch, etc., all these are essentially part and parcel of the supply side management strategies, in which we bring in new generator unit commitment, economic load dispatch. Obviously, all these are part and parcel of supply side strategies, in which we switch on and switch off the generators based upon the demand. We ramp up and ramp down the generators based upon the ramping requirements in the system. So all these strategies are essentially supply side management strategies. And now, moreover, the focus is, since a lot of renewable is getting penetrated in the system, the supply side management strategies have become even more critical, wherein some of the services, you see the problem. When we've got one part is system has got deregulated, in which the generators are essentially not obliged to provide all the demand. So the system operator is responsible for providing the demand. So now, if
Yes.
there is any contingency, system operator has to run after providing providing that power. And now the second part of the problem is, because now originally the focus was only on power, all ancillary services like reactive power, like ramping, like inertia, etc., they have to be provided for separately, and there is no mechanism to do that. So the challenges on the supply side are not only critical, but they would evolve also.
Yes.
Supply side mechanism, just in the way by which we have got demand side management mechanisms, in a similar way you could classify supply side management mechanisms as well. And in those, economic dispatch and unit commitment would be fundamental to those supply side management mechanisms. So if you are presently asked to identify what are the supply side management mechanisms, starting from those, you could have n number of other mechanisms. The challenges would obviously, markets are one of those. The challenges would obviously be because of the new challenges would be because of the renewable penetration happening in the system.
Yes. Thank you, sir.
Any other question? Sorry for interruptions. In between, I have to take some urgent calls as well. So, any other further question before we move ahead? If none, we move over to the scenario to understanding the communication architecture for providing demand response. We all understand a lot of smart meter rollout is happening in the country and across the world. These essentially have the potential to provide significant demand response in the system, and this the providence of this demand response is essentially would be facilitated significantly by the smart meters and two-way communication happening between the consumers and the grid. And to do that, obviously, what we need is appropriate communication architecture in place. So this is one of the broader facets that we can visualize as of now, in which we would have the demand response loads, load aggregators, and the utilities participating on the other side, and data concentrator units providing the data, concentrating the data coming from the various demands. Energy management system comprising of smart meters, and obviously the meter data management system and demand response automation servers. These are the type of talks, these are the type of frameworks that we have been talking about, which would facilitate the architecture for providing demand response. So if you see, if we touch upon each one of those, demand response loads are loads which are amenable to provide demand response. Aggregators, which would obviously aggregate the demand responses from the different loads. Utilities, who would essentially benefit from the aggregation being done by the aggregators. So these would be communicating with customers. Demand response loads would be communicating with the data concentrator units, which are localized units, compiling the data of all the demands in a specific geographical area. On a larger overarching picture, we would have energy management systems, which would manage the system demand, which would provide appropriate signals to control the demand and the generation for appropriate balancing. This would obviously be facilitated by the meter data management system, which is a part of the AMI system that we are installing, which essentially captures the meter data consumption at captures and stores and processes the data that is being generated by the smart meters in the system. Demand response automation server is a new mechanism or a concept that is coming up, in which those demand response loads which are willing to provide demand response participate in the server through the aggregators and provide demand response in the system. Obviously, there is a lot of communication architecture that would be required. If we get into the details, you would have the for providing the demand response, you would have the demand response automation servers based upon a wide area network platform. On the other side, when on the household side, we would have, if you want to control the demand on the household side, you would have HMS with monitoring devices like ISD, home energy gateways using different communication technologies like cellular, WiMAX, etc., depending upon what type of system you have got, so and so forth. You can obviously, from the household side, you can have home area network. From larger system perspective, you could have a wide area network to provide that demand response. The communication infrastructure is obviously similar to what we adopt for the overall distribution system. So if you have in a distribution system, if you have a wide area network to capture the data from those smart meters, home area networks to manage the demand at the household level, remote users like smartphones and laptops we could observe using internet, neighborhood area network for one house to pass on that information from one house using a NAN gateway to a data concentrator unit, which essentially which communicates with the wide area network and provides those services to the system operator or to the market uh, as a whole, maybe directly or through an aggregator, depending upon how it is participating in the market. So there are various layers and levels at which different stakeholders, houses, and upwards would participate in the demand response programs. Available communication options at the local level, either it would be the home area network, LANs, and those at a higher scale, it would be neighborhood area network, and still higher scale, we would have wide area network. The things that we need to understand is what are the coverage ranges. The home area networks obviously have got home area networks or building area network. They would have smaller coverage, and as you go higher up, the coverage range would increase. And also the data rate at which you would be operating. At the household side, the data rate is significantly low, while when you go to the wide area network, the speed at which you require the data to handle the system would obviously increase, because in that case, you need a real-time monitoring and control in the system. Looking at it from another perspective, the energy efficiency measures, they are the mechanisms which operate on a very long-term time frame. As you go up, time of use, time of day tariff, they operate in hourly time frame. Daily peak load management, they may be operating in hourly to minute time frame. Day ahead demand response can operate in a relatively shorter term time frame. Real-time demand response, again operating in minutes or seconds. And spinning demand response, it is a fast demand response operating in seconds or milliseconds. These are the time frames in which different demand response programs act. And as the time frames increase, as the time frame becomes shorter and shorter, there is an increased interaction with the grid. Obviously, these are the services which are more critical, and they require fast response in the system, the shorter term time frame services. And obviously, they'll require an increased level of control and speed when we are providing those services for shorter term time frame. Any questions up till now in this case? If none, we move ahead. Yeah, please. Anybody has got any question on this?
Sir, spinning reserves, how they offer demand response by providing kinetic energy to the system and drawing kinetic energy in that manner, or any other techniques are there?
Spinning reserves are usually provided by generators, but whenever there is a requirement in the system which is not, the generators are not able to provide those, obviously spinning reserve has to be provided in a very short term time frame. So all
Yes,
sort
sir.
of demand response programs which can help. So whatever you have on the generation side, same time skills you have got on the distribution side as well. So
Yes, sir.
whatever programs can provide demand response from the customer side in that time frame would constitute, let's say I've got a battery storage facility and I'm willing to provide instantaneous demand response, maybe, and
Yes,
something
yes.
of that sort, in which all those services which are willing to provide, which are available on a very short term time frame, which are willing to respond in a very short term time frame, as well as which are which are not only willing, but they have their capacity to provide those services only for a short-term time frame. Those services can be provided either through market or through aggregator or directly as well, depending upon the size of the customer.
Okay. Thank you.
Sir, I have some query about energy efficient we were talking about for demand response.
Which one?
So energy efficient devices or technology. So there is a concept what we have seen the foreign countries are applying, that is net zero energy buildings, where the construction of buildings as well as in a cold places geothermal energies are being used to keep warm. So those are possible in this demand side management. If we construct a home, it could save more and more energy.
Yes, yes, we can do it. Um, Actually, it all depends upon the type of philosophy you would like to adopt. If you're talking about net zero homes,
Yes, sir.
there are people in the country who are talking, in India, people are talking about net zero cities now. There are. So it is all about, let and if you understand it very clearly, it is all about identifying the scale at which you would like to operate. If you would like to operate at a house level and make a house net zero, obviously the cost of doing that would be significant. If cost of that would be significantly high vis-a-vis the cost of making the city net zero.
Okay.
If I'm comparing, let me make it very clear. Let's say if in a city there are 1 lakh houses, and if you want to make all 1 lakh houses net zero, individual houses, obviously the cost of those net zero houses, individual net zero houses, would be much more than making the city as a whole net zero.
Yes, sir.
So depending upon the type of funds that are available with you, you could either target net zero houses or net zero cities or a net zero country as well. And obviously managing on a larger scale would be easier.
Yes, sir.
Managing on a larger system scale would be easier. However, in that case, the cost of network comes into picture. Very simply, I'll explain कि अगर मैं अपने घर को, if I want to make my house net zero, obviously I don't require a network to connect to the grid.
Yes, sir.
I hope I'm clearly audible.
Yes, yes, sir.
If I want to make my house net zero, I don't need a network to connect me to the grid, in which case the cost of network would be significantly reduced. However, if I want to make my city net zero, obviously I'll have to have a network with between the different houses, in which though the cost of energy would be significantly reduced vis-a-vis making individual houses net zero, but on the same at the same point of time you'll have to may have interconnection between the houses so that the overall city becomes net zero. And when you compare that situation with a at the national level, if you want to make every city net zero, you can do that. In which case, you will not require network infrastructure between one city and another city. But then the cost of making individual cities net zero is much higher as compared to planning for a net zero country as such. So, from those perspectives, you have to decide and design different net zero strategies, whether you want to do it for at the household level, at the city level, or at the national level. It depends how much funds you are available and how would you like to design those strategies. As a country, what we are presently focusing upon is to create net zero at the national level, so that resources from different parts of the country can be utilized and optimized, such that system emission efficiencies are managed. I hope that answers your question.
Yes, yes. Another is we have also heard that we are planning to have a parallel grid of solar with the present grid what traditional grid we have. Is it in a working
No,
phase?
no, it is not something that we want to have a parallel grid of solar.
Okay.
It is only that we are trying to put in lot of transmission lines, green corridors we are trying to come up with, essentially to evacuate the power from areas where there is a lot of renewable energy, solar energy being generated. So
Yes.
green corridors are essentially, it is not something in parallel to the existing grid. It is very well integrated with the existing grid. However, it is not a separate grid. It is a part and parcel. However, new corridors are being installed such that evacuation of power from those points where there is a lot of solar generation available to the demand side can be done.
Thank you, sir.
Okay. Any question? Anybody else? If not, I hope everybody is able to understand what demand response mechanisms, demand side management strategies are.
Yes, sir.
Okay. So these are all the facets there. What thing that we need to understand is there are market frameworks, there are regulatory frameworks that we need to talk about. There is a communication architecture that has to be embedded into the system. There are different type of stakeholders that have to be brought into picture. So when we talk about demand side management, obviously we need to touch upon all those facets. We need to touch upon all those facets and design our systems accordingly, both from a regulatory perspective, from a technical perspective of creating appropriate communication, to market perspectives of creating appropriate markets for demand response to participate, and for appropriate classification of customers. So all these form a part and parcel of the demand side management mechanisms. It is not only providing changing the demand, there are various facets attached to that. Like say we talk about aggregation from the distribution side. Distribution company in itself can be the sole aggregator for providing demand response, or there could be uh, subsidiary, I would say, what I would say, subsidiary aggregators below the main, I would say, below the meta aggregator distribution companies. There are possibilities of that, in which case aggregators participating below the distribution companies, talking to the consumers and providing those aggregation services to the distribution company, they could exist, or a mix and match hybrid model of the same could also exist. Demand response deployment. This is one of the examples that we have secured from the utility, one of the utilities in Delhi. This is how they deploy demand response. The utilities, they notify certain events. There's a demand response automation system. They give a signal to the demand response controller. It executes the load shedding. This is one way. Or through the meter data, MDMS, it passes on certain information and depending upon the availability, it uses that information to develop an appropriate demand response signal. So these are some of the use cases that we can highlight. This is another substation connectivity for providing auto demand response. These are the present architectures of how utilities, some of the utilities, they are operating to provide demand response in the system. And obviously, the sequence of events in the DSM cycle, the load research and market potential assessment. First thing, when we want to provide demand response, first thing that we need to do is identify the potential of demand response that can be secured from different stakeholders. That is the first shot that has to be done. Thereafter, appropriate planning has to be done, and a program has to be designed to develop appropriate sequence, to develop an appropriate strategy, to develop an appropriate program for demand response. And once the program is implemented, then an appropriate evaluation of the program and recalibration of the program is to be done. So it is not a simple one single thought. There are various stages of applying any demand response or demand side management system. As far as the present application scenario is concerned, some of the states, they have already adopted some or other demand response mechanism. These could be in terms of time of day use tariff, etc., or others as well. But the industrialized states, they are focusing more on demand response strategies than the non-industrialized states. So this is a reflection of the states which have already adopted time of day tariff for certain type of consumers. So the green indicates where industrial and commercial consumers have been offered time of day tariff. There are other states which are only industrial consumers have been offered time of day tariff, and so on. So you can see a majority of the states, they have adopted one or more form of time of day tariff for one or more type of customers. There has been some new strategies, some new pilots that have been adopted for creating demand side management over the last decade. If you see, the aim was, we must understand there are a variety of aims in providing demand side management, and some of those aims could be to reduce the peak demand. So in 2014 and 2021, the utilities have adopted some demand response mechanisms to reduce the peak demand. Similarly, on providing mechanisms to deviate from the schedule. So to develop such mechanisms, some of the utilities in Delhi and Rajasthan, they also have developed demand response mechanisms. Uttar Pradesh, Maharashtra are other states where peak demand has been focused upon for the pilot projects. Internationally also, several markets like California market, PGM interconnection, they have adopted demand response programs for providing different type of services. The type of services vary therein. They could be participating through capacity markets, emergency demand response programs, or ancillary demand response programs. Similarly, in other countries like Australia, reserve capacity delivery, incentive-based participation, and so on. Recently, they have also started talking about virtual power plants. So there are a variety of ways, mechanisms by which demand side management is being piloted, experimented to understand what is the potential of each such project. Any questions till now? Else we move ahead. One innovative thing that we have proposed, maybe if you have heard of, I'll not go into the deep of this topic, but to enable you to understand the potential of quality regulation in providing demand response, I'll touch upon. Demand response obligations is a mechanism that we have proposed similar to renewable purchase obligations. So while there are, if you have heard of renewable purchase obligations for the utilities to purchase a certain quantum of power from renewable sources, similarly, the utilities can be pushed to provide demand response from demand response in the system. Certain quantum of demand response they can be obligated to provide, such that the systems, so that everybody participates in that demand response program. I'll just show you one of the examples. Presently, the barriers in providing demand response, if you all understand, there are not only technology barriers, because communication has not happened in that big way, which should have happened. That is one of the reasons why demand response or demand side management has not picked up as yet. The other facets include economics, because there is an inappropriate market structure, inappropriate money being offered for providing that demand side management strategies to participate in that demand side management. Essentially, those are non-competitive offers. So consumers essentially do not participate. Another reason is that the regulatory framework is not so strong so as to enforce demand response mechanisms. That is another challenge in the system. And yet another challenge is there's a lack of coordination between the consumers and the utilities. Appropriate coordination, and there's a lack of understanding of the consumer behavior as well. So there are a variety of challenges. If you see this slide thoroughly and try to understand, there are a variety of challenges which are essentially behind the weak demand response mechanisms in the system. These are the reasons why demand response or demand side management strategies could not be successful in most of the countries across the world, and specifically in India as well. If anybody has any question on any of the points, if you want, I can specifically repeat or maybe focus on one or more of the points. But this is all that essentially reflects why demand response or demand side management strategies were not successful over all these years. And they include poor technology, poor communication, poor economic values that the customers are able to secure for participating in the markets, for participating in the demand response markets, lack of appropriate regulations, lack of appropriate coordination between different stakeholders. These are the four facets which have limited the ability of demand response programs to act. In order to mitigate these challenges, we have proposed a demand response obligation mechanism and similar to renewable purchase obligations, in which those entities which provide demand response would be offered demand response certificates in a way similar to that of renewable energy certificates, which is being done for all renewable generation as on date. These these demand response certificates could be traded in the market in a similar way as being done for renewable purchase obligations. Exactly the same way, the assessment of current demand response has to be done. Obviously, that has to be done. The mechanism is first to assess the current demand response deployment from different demand response sources as a percentage of total energy resources, examining the historical growth of demand response, identifying the drivers behind the growth, analyzing whether the identified potential has been met or not, progressively increasing the demand response targets to align with the national objectives. So as more and more renewables come into the system, we'll have to have higher and higher demand response targets as well. So on and so forth. This is how a demand response obligation program can be run, in which the entities which provide demand response, they get a certificate. The demand response is aggregated by the aggregator or the consumer. It offers the demand response to the grid. Those certificates can be traded. They get a value for providing demand response, and the grid is able to fulfill the demand response targets that has been set for it. This is how a demand response obligation program can be operated such that all stakeholders can participate in that. And obviously, to certify or verify whether the demand responses have been provided or not, we would have a certain verification process to provide that demand response. All demand response certificates would be registered in a central registry, depending upon what is the quantified certificate that they've got for every unit of change in the electricity uses that they are providing. Any questions on this thought? Because this is something different from the conventional mechanisms. If not, we move ahead to understanding the new opportunities that are coming up when we are installing smart meters. So understanding our ability to analyze that smart meter data for providing demand response. What is happening as on date is we are moving away from conventional meters and we are putting in a mechanism of advanced metering infrastructure, in which we have got two-way automated meters which can do outage detection, which can do distribution control, which can provide demand response. Smart meters obviously are a part and parcel of that. It provides an interactive display and has got a physical or a wireless connection. This is where we are heading towards with the rollout of smart meters. Smart meters, they do a real-time data collection. They have an automated communication. They are able to provide consumers with an engagement. So we have appropriate tariff and incentives in place. Those smart meters can provide real-time demand response into the system. They can provide that flexibility and become a part and parcel of the energy management system to balance the demand and supply imbalances. The applications that are presently not developed and are yet to be developed would obviously be dependent upon the large quantum of data that would be generated in terms of the energy consumption, in terms of voltage, current, power factor. So the type of applications that we need to develop is load profiles, load forecasting, load demand response estimation, scheduling the load shedding, tariff management. These are the type of typical applications that can be developed. Obviously, the challenges would be to handle the significant quantum of data that is being generated, to understand the consumer's behavior, which is presently unknown, and to correlate their consumption time and different time scales. These are some of the challenges that would arise, that would obviously come up as as we would try to develop applications from those smart meter data that are coming up. Solutions would be dependent upon a lot of data pre-processing and clustering of the information that should be available to us. So to process all that data has to be pre-processed, it has to be cleaned, it has to be normalized, and based upon certain clustering mechanisms, it has to be clustered to calculate what for each customer type, what are the demand response capacity, what are the demand response potential existing in those customers, how much they can provide demand response, and so on. Obviously, all this depends upon the consistency of the user's consumption habit. So the user's consumption habits are consistent, they can be of value to providing demand response. And for that, you need to analyze the customer's load profile characteristics such that they remain consistent over a period of time. Obviously, all these residential consumers, if they are made a part and parcel of the demand response mechanism, they have got a significant amount of, they'll have a significant data set, and the potential of those is significantly high, provided we are able to analyze their behavior, provided we are able to cluster them appropriately. Once we have that smart meter data in hand, we can identify the target customers or the set of customers by classifying the customers accordingly and identifying the demand response potential of each customer segment separately, engage those customers, devising different strategies for different type of customers, and designing appropriate demand response programs for each and every type of customers in the system. Any quick questions on this? Anybody has got any quick questions on this? I'll be happy to take up those. I hope everybody is listening to. We have got 16 participants as of now. Dr. Nishant, Gaurav, Jasmine.
Hello. Yes, sir.
Yes, sir.
I hope you are able to follow what I'm talking.
Yeah, yes, sir. Yes, sir.
Any questions if you think?
Sir, if you can take up one use case of, in the previous slide, you explained the challenges and the solutions that can be provided. Maybe you can take up one use case and discuss that in detail, like forecasting or
This
especially
slide?
the challenge. This one.
Sorry.
Applications, challenges, and solution. Smart meters.
Application challenges and solutions. So applications, obviously presently one use case could, if you see the applications, there are 4 or 5 different applications that we are talking about. Load profiling is one. Presently, what is happening, a very first set of application that would evolve in this case is, presently, if you just Google and see what is the load profile of a residential consumer in India, you'll find a typical load profile. I hope you'll find it. There would be a certain graph that you would see that what is the typical load profile of a consumer. That load profile is essentially based upon, if you see, there would be some sort of a duck curve available of reflecting the load profile of a residential consumer. You will be astonished to understand that the load profiles that we use today in 2025 for designing the tariff for the residential consumers, the load profiles were designed somewhere in 1970s. So we are still using the same load profiles which were designed in 1970s, and presently we are using it. Presently we are using it to design the tariff for present day consumers as well, despite knowing it very well that the consumption pattern of households has evolved from 1970s to 2030s. Over the last 50 years, the consumption pattern in terms of air conditioning load, in terms of lighting load, in terms of all other loads in household has changed. So by using a smart meter data, you can reclassify the customers based upon the type of profiles that they've got. So you as a customer would have a different load profile than me as a customer. Though both of us may be classified as residential consumers, but our profiles may be significantly different, in which case you and me should not be charged a similar level of tariff. It may be possible that your demand is significantly happening at that point of time when the system peak is there, and my demand is happening at the point of time when the system peak is not there. So obviously your impact and my impact on the grid would be different, in which case the tariff should be different. And in order to do that, essentially you need to reclassify the customer, you and me, in separate classifications, depending upon the profiles you fit in and the profiles I fit in. This is one first sort of example that should be done.
So, if I may interrupt you, will that call for like further subcategorization or classifications to be developed? Like I and you both
I
believe?
would say not only further classification and subclassification, I would rather use a term that you have to do away with the present classification and develop new classifications as such. You
Okay.
understand the situation that it may happen that your demand profile matches with the demand profile of a commercial consumer or that of an industrial consumer.
Okay.
In which case, why should you be classified as a residential consumer in case your profile matches with that of a commercial consumer? Your charges should also be reflective of the profile demand that you've got, which is reflective of that of a commercial consumer.
Okay.
This is the
Got
point.
it. Got it.
No?
And another angle to it is as a retail consumer,
Hmm.
can I take advantage of the data which my smart meter collects and tune my load or my demand from the network to benefit me?
Exactly. You are at the very correct point. You can very well the home automation system, the home energy management system that you would design, you could easily develop an optimization algorithm to operate the devices in your houses in such a way that your the devices they operate in an optimal way depending upon the price signal from the grid and the price signal that the smart meter receives. So if during the daytime the prices are high, obviously your smart meter would give a signal to the specific device not to be operated during those hours. Or at least you will understand that if you're operating your devices during those hours, the cost of operating that would be significantly high.
Mhm, mhm.
Is that fine?
Yeah, that explains that the reasoning and the motivation as well. But is such kind of differential pricing based on time of day, is it currently in use anywhere, at least in India?
It is only being used in the case of industrial consumers, not for the case of commercial and residential consumers. However,
Mhm.
the problem now is that because of the opportunity and problem, the opportunity is because of the smart meter rollout, and the problem is because of significant RE penetration happening in the grid, which essentially provides solar. If you talk about solar, solar is coming up during the day hours, and the demand uh, during the evening hours is not being met by any of the generators. So it is leading to a significant ramped up demand during the evening hours, which essentially uh, is pushing the utilities to think about it. I'm not saying that they have implemented it, but they have vigorously started thinking about it.
Okay.
And that is where the opportunity lies in. I
Got
hope
it.
that answers your question.
Certainly, sir. That's insightful. Indeed. Thank you.
There's a lot of depth in the slides that I'm presenting. Obviously, if you understand, if you are able, if you have an interest, we can go deep into any of the topics of your interest. I think, yeah, we were at this point. This is the point that I was trying to explain, in which we classify the customers for demand response. Now I think this slide would be more clearer to you. For whatever I have discussed, we identify the customers for demand response based upon not only their load profiles, but on their potential to provide demand response in the system. That is what would bring value, that if there are certain consumers which can provide more demand response, you can again classify the customers based upon demand response capabilities rather than classifying them as residential, commercial, or industrial consumers. I hope that gives you a thought process, Ishant. Customer classification obviously would it is a detailed process. You have to take into consideration several factors. Their characteristics of the customers, profiling of customers has to be done on various time scales and so on. So there is certain depth into this, different mechanisms to monitor the load. I'm not going into the details. There's a lot of depth in this. I'll take a short break of 2 minutes. I'll just have a glass of drinking water and then I'll come back. So I'm back with another session on cybersecurity perspectives. We've touched upon in 2 hours, we've touched upon what are the demand response strategies, demand response mechanisms in the system. Another topic of key interest in the grid is that of making the grids smart grids and the evolving challenges of cybersecurity. I hope there will be interest in the class to understand this facet as well. Anand, Ankit, if they are there, if they are listening, Jasmine, Jayant, any one of you, is anybody working in this segment on cybersecurity? If anybody has got any basic understanding of what the cybersecurity challenges are and why do they come up? None. Okay. So this is a very introductory lecture on what smart grids are and what are the cybersecurity challenges, evolving cybersecurity challenges in smart grid scenario. And how do we differentiate these from the conventional cybersecurity challenges? So, friends, what essentially is happening in the grid is the grid has got, traditionally the grid was being operated as a grid in which there was a centralized generation from the generous transmission system to the distribution system to the end users. What has started happening over the last decade or so is we have significantly started focusing on improving the efficiency of energy supply systems, about increasing the reliability of electricity supply systems, enhancing the consumer engagement, and also focusing on significant RE penetration. So the traditional grids are evolving towards what we call as smarter grids, in which the portfolio of generation is changing. There are a lot of interconnection happening and a lot of local generation happening in the system and a lot of renewable generation happening in the system. This is the major change that is happening on the generation side, and on specifically the quantum of local and renewable generation is increasing like anything. That is a major change that is happening in the grid. Local generation to fulfill the local demand or captive demand in the system, renewable generation, specifically wind and solar, providing possibly helping the grid to be decarbonized to the extent possible. On the transmission side, the changes that are happening to make the grid smarter, we are having better remote control mechanisms in which the substations are being operated from remote control centers. We are going in for wide area monitoring systems in which the control room is able to monitor and observe the substation parameters on a wider scale. Then there are mechanisms of there are intelligent substations coming in. Power Grid has installed a lot of intelligent substations in which they are able to make decisions on their own. Grid automation is happening in which fault detection and reclosing and healing is happening on self decision making algorithms, smart switching, smart distribution systems. These are all what are evolving on the transmission and the distribution sector. On the residential side, we have started using more and more smart meters, energy storage is coming up, home display units are coming up where we can see the energy consumption of individual components, individual devices in the house. On the commercial and industrial side, we are having EV charging facilities, we are having distributed energy management systems, smart buildings are coming up. So these are the changes from the perspective of communication side, from the perspective of technology side. New technologies are being adopted to make the grid smarter in a sense that our observation at various levels and the ability to control the components at various levels, that is changing. This essentially is because of the development in the communication technologies that has happened over the last 2-3 decades, and the ability, the cost going down, and the ability of the power system engineers to identify the use cases for making the grid, making remote control of the grid, remote observation of the grid possible. That essentially is coming through smarter communication technologies. What changes are happening in the grid? Essentially, the grid, rather than being operated through electromechanical systems, now it is being operated through more and more digital systems. Rather than providing one-way communication systems, now we are having systems in which the other side of the node is not only providing you the information, but you are also able to control that component. So essentially, you are providing two-way communication in which this control room operator is not only securing that information, but is also passing on the control signal for those components to be operated. Earlier, it was more about centralized generation, large power plants. Now it is more about distributed generation, small power plants, renewable power plants. Earlier, there were less sensors in the system, less monitoring in the system. Now there are sensors throughout the system, at transformers, on lines, on substations, a lot of substations in and around the power systems. Earlier, the monitoring was manual monitoring. Now it is self-monitoring. The algorithms are built in place so that if the parameters go beyond the design parameter, the system starts reacting to that. Earlier, we used to have manual restoration in case of any fault. Now the healing is happening on a self-contained basis. The system in itself operates the reclosers, operates the circuit breakers such that self-healing is made possible. Failure and blackouts was a common feature now. Now, instead of having failures and blackouts, we are shifting our strategy such that adaptive healing or islanding is possible for those power systems. Essentially, all those features lead us to a situation where rather than having a limited control, we are having pervasive control in which the control algorithms are able to see, the control room is able to see deep inside into your houses as to what is your consumption pattern and what is to be controlled and what is not to be controlled. Along with that, the markets also offer an opportunity because now we have got more and more choices vis-a-vis the earlier situation in which our supply system was dependent only upon a single choice set. So a two-way communication system allows the customers to interact with the utilities, enables faster decision making. Self-healing capability, it detects and isolates the faults, restores the supplies with minimal human intervention. Real-time monitoring and control tracks the power quality, load, and voltage in real time, enhances the grid reliability, it reduces the losses. Integration of renewable energy, it is supported through various sources. Challenges are in forecasting and storage to handle that variability. Customer participation, it enables customers to act as prosumers, to generate electricity, to be producers at times. It gives them active customer participation, allows them to control the load, allows them to go in for peak shaving and provide demand response. AI obviously an integral part of that ecosystem in which the smart meters provide the real-time data uses for the data. It enables remote reading. You don't have to visit the site and do the meter reading. The meter reading can be done by the control room personnel sitting in his control room because the data is getting transferred on a real-time basis. There are electric vehicles around which can act as storage units, helping to balance the demand in the system. There is distributed generation in the system, which would eventually help to meet the local demand, reducing thereby the transmission losses in the system. A lot of automation in terms of sensors, AI, control system. These things are getting embedded into the system. More and more algorithms, more and more computers, which help to monitor the systems, which help to control the different components in the system. That is what is getting evolved into the power system as of now. To understand the changes happening, why these changes are happening, and what are the facets of these changes, who all are the stakeholders in these changes, and whose interest has to be taken care of. So when we use the term smart grid, we obviously have to I'll just take a quick break. Just give me a break. Yeah, anybody has got any quick questions?
Sir, which component is most vulnerable to cybersecurity challenges?
Which
Phasor data
component
concentrator.
is most
Phasor,
Hmm?
is it phasor data concentrators or PMUs or smart meters?
Actually, vulnerability is not you cannot quantify it in one sense. Vulnerability from the smart meter side is the easiest one. However, you can penetrate the smart meter very easily, let's say, but the impact of doing that would be very low. You can, at max, what you can do, you can control the power flow in a house. So for
Yes, sir.
anybody to have any interest in penetrating into the smart meter would be low. So despite that it is the weakest link, the interest for anybody to penetrate into that would be lowest, and so on and so forth. Yeah, please.
If someone accesses like phasor data concentrators, he can get a overview of the topology of the network, where the power comes and where the power goes, and all this is a security threat to the grid.
Obviously, very correct. So the higher at the higher level, the higher level you operate, the risk of intrusion would become higher. So if
Yes, sir.
somebody is able to penetrate the higher level of the system, in which the impact on the system would be on a larger system or larger customer set, obviously um, those are more riskier options. Those are more risky situations. However, because everybody understands that, so the cyber security measures at those levels are obviously higher. The smart meter may be easy to penetrate, but not the phasor data concentrator. No, and not the meter data management system. So you can, while you can enter the smart meter, but you cannot enter the meter data management system. You can control the smart meter, but you cannot control the meter. MDMS, entering into MDMS may be difficult. So,
Okay.
um, um, and obviously getting penetration into the MDMS through the smart meter is not easy, because the data is cleaned up before it can be processed further. So understandably, the points which are more prone to cyber threats are not the points which are most impactful. And those points which are most impactful are obviously being protected with the higher level of cybersecurity.
Yes, sir. Thank you, sir.
So before we get into the details of the vulnerability cases, I think it would be from a very generic perspective, it would be of interest to all stakeholders to understand who all are the key stakeholders in this smart grid phenomena, in this smart grid ecosystem, and what are their perspectives, so that while we are designing any cybersecurity mechanism, we understand what are their perspectives, based upon which we start taking a design decision on how smart grids are to be designed such that cybersecurity does not become a challenge for them. In this case, these are the different stakeholders: transmission, generation, distribution customers, the service providers, the operators, then the market. And the communication flows are indicated in blue lines. You can see communication flows happening between different stakeholders. The electrical flow happening between transmission, distribution, consumer, generation. The electrical flow does not happen with the markets, operators, or the service providers. They only have the communication flow. Taking up each stakeholder separately, first is that the case of a consumer. Consumers, obviously, as we just discussed, there are a variety of consumers, and these consumers, they can provide those services as we just discussed. These home consumers, they would home consumers or industrial consumers or commercial consumers, they would provide, they have their own set of components, own set of communication requirements, and each set of consumers would provide some sort of services to the grid or interact with the grid for securing services from the grid. It could be through the service providers, it could be through the operators, through the distribution companies, or from the markets. So all these stakeholders, different stakeholders, customers, they would require continuous interaction with those stakeholders like service provider, operator, distribution company, or the markets. And within the premises of each stakeholder, like the home, the industry, or the commercial building, they would have their own internal communication infrastructure and own power flows happening in the system. So, depending upon the type of consumer, the network infrastructure as well as the communication infrastructure would vary. So while it is simply a smart meter and some few appliances and some automation algorithm being adopted along with the thermostat to measure the temperature, in the case of a home area network or a household, the same for the industrial consumer would be slightly different depending upon the what type of components it is coordinating with. And the case of buildings, it would be even more different, or commercial setup, because the components, individual components would be behaving in different ways. So in a building, every house would be a different unit to be controlled. In the case of a commercial building, every shop or a commercial establishment is a different entity to be monitored and coordinated with. So these are the generic perspectives that one needs to take care while designing a smart grid system. From the market perspective, there are different stakeholders like service providers, transmission system customers, generation is there, distribution is there, and operators are there. They all participate in the market, and you require appropriate communication infrastructure between those players and the market framework, market players. In the market, there could be market operation, market management, DR integration, retailing, ancillary operations, trading, wholesalers. So all these form different nodes in the market, and they need to interact with different stakeholders in the system. All that information about prices has to be passed on from those stakeholders to the from between various stakeholders from the market. Similarly, the service providers like retailers and aggregators, they also have their own ecosystem in which they would have billing, customer engagement, account management, home management system, building management, installation management, maintenance. So all these form a part and parcel of the activities that the service provider has to do. They, in order to provide those services, they have to interact with the operators, interact with the markets, interact with the customers. The type of services, billing, smart building management, etc., all these services, they are a part and parcel of the services that the service provider provides. From the operation perspective, um, the system operator has to provide, has to interact with the all those stakeholders, managing the operations, managing the planning, managing the real-time operation, maintaining the records, processing the meter data, processing, having a communication network in place, having appropriate security system in place. So this is from a generic systems operation mechanism. Network operations, again, in terms of load control, managing the faults at the local level in the distribution system, controlling, analyzing those form a part and parcel of the system operation mechanisms. Smart grid operations, they'll require communication interfaces with other domains. Network operation is it is required for metering, recording, and analysis of the data. Real-time information exchange with the power market needs to be established. So with the markets, they need to interact on a real-time basis to provide that information. The operators, they interact with various service providers. These operators, they'll interact with various service providers in the system to provide those services. And obviously, in all these cases, information exchange becomes the key process that is to be done. Similarly, because of the large number of generators that are coming up in the system, not only power flow is happening, but significant internal communication mechanisms have to be established. Control, measurement, protection, recording systems have to be put in place. External communication with the operators and the market players have to be done. So this is again a perspective that has to be kept in mind while designing smart grids. From the transmission system domain, also for the transmission system control, measurement, protection, recording, stabilizing, optimizing, all these form a part and parcel of the activities that the transmission system has to do. Again, they have to interact, the transmission system has to interact with the generation, operation, markets, and distribution. So information exchange has to happen at that levels as well. On the distribution side, again, similar challenges, similar architecture is required as that of a transmission side, in which there are internal networks involved, and within the distribution system, control, measurement, protection, etc. Those activities have to be performed by the communication system, and interaction at the higher level between the operators and the distribution system owner that would always be there. So again, we come back to the same basic question as to what a smart grid is. A smart grid is essentially a conventional grid with more and more embedded communication infrastructure, more and more embedded communication infrastructure to provide support for the information to be transferred from one node or one stakeholder to other nodes and other stakeholders. So essentially, it is an embedding of communication infrastructure within the power system infrastructure to enable the information to be transferred from between different nodes. So essentially, it is a marriage between the electrical infrastructure and an intelligence infrastructure comprising of communication as the key component of that intelligence infrastructure, so that these nodes in the system, these nodes in the power system can be appropriately observed and controlled. To understand this juggernaut easily, essentially what we need to do is we need to identify who all are the key components, what all are the key components in the system. So the key components in a smart grid system are essentially generators, transmission companies, distribution companies, distributed energy resources, customer premises. These are the key domains, key components of a power, key domains of a power system as such. These are the component layers. To communicate between these nodes, between generation, transmission, distribution, you need to have an appropriate communication layer. The communication layer essentially provides communication between the same nodes that exist as a component in the power system layer. Based upon that communication layer, we have an appropriate information layer as well. Information layer gives us an understanding of what type of information is being generated, what type of information is being processed from one component to another component. Obviously, this information layer passes on the information from those components, from one component to another component through the communication layer. So for that information to be processed, you need to have appropriate communication layer in place. And that communication layer should be such that it is able to connect with one node, connect one node with another node in the system. On top of that, we have got function layers. So information defining which information would flow from which component to another component, would depend upon what type of functions you want to create, what type of use cases you want to create. So depending upon the type of functions that you want to create, your information has to be processed from one node to another node. And depending upon the information that is to be processed, you have to have an appropriate communication layer being installed. So all these, and again, the function layer, the type of functions that you perform would depend upon the business layer. Business layer obviously defines what are your business objectives, whether it is political, regulatory, within the political and regulatory framework. What are your business objectives? What are the services that you would like to provide? What are the services that you would like to secure? What is that you want to sell? What is that you want to buy? Based upon the business layer, you define different functions and keep what all are the functions. Let's say if as a janitor I define that I want to sell power, so my function is to sell power, based upon which I need to have an appropriate information layer, which would flow over the communication layer to provide the janitor for an appropriate provide the janitor with the facility to uh, inject power into the grid. So depending upon the type of business that I have for myself, I have to design certain functions which I should be allowed to do, for which information has to be processed from one node to another node over the communication layer for the different components that are visible here in the slide. Does that make sense for you? Or if there are any quick questions? Guys, anyone? If you have got any quick questions, we'll be happy to take up those. Any quick questions from anyone? I hope not everybody is sleeping. Anyone? Ankit, Jasmine, Jayant, Lakshmidhar, Shirisha, Subrat, Koteshwara, Ujwal, Virendra, Yangadatta. Is everybody sleeping or somebody is able to follow me what I'm speaking? Guys, it seems like
Following, sir.
Yeah, please. Please go ahead. If you have any quick questions.
We are following you, sir. No questions from my side. Yeah.
Okay. Thank you. In that case, we move ahead to give you an understanding of what smart grids are. Essentially, they are, as we just discussed, embedded communication with the power systems. When we have got embedded communication with the power system, obviously, as the nature of the power system varies from generation to distribution, generation to transmission to distribution, to localized household networks, household electricity networks. In a similar fashion, as you saw in the last slide, you have to design communication protocols, you have to design communication architecture, which aligns with the physical power system architecture. Since in the case of power system architecture, in the transmission system, the transmission towers are far away from one point to another point. The typical type of network that we adopt for transmission system is a wide area network, which is able to capture information from a wider geographical area and process that information at centralized servers, which could comprise of mechanisms like EMS, SCADA, mechanisms like distribution management system, MDMS, outage management system, demand response systems, using communication operations, using customer engagement protocols like call centers, billing, and all these separated from the communication channels, communication infrastructure architecture on the transmission system by certain firewalls. In the case of distribution system, instead of having wide area networks, you could have certainly field area networks in which the communications can be done with nodes which are relatively closely placed, like commercial consumers, industrial consumers, and distributed generators. So there, the type of communication architecture used is slightly different from that being used in a wide area network. And to a similar extent, in the case of a home area network, where the components like EV chargers, display units, HVAC, water heaters, they are a part and parcel of the same house. So there, the communication protocols, communication mechanisms would be slightly different. So these could possibly be having Wi-Fi. These could be operated on a Wi-Fi system, on a VoIP system, IED, using IEDs, CCTVs, RTUs, etc. So depending upon the type of power system that we are handling, our communication architecture would vary accordingly. In the case of transmission system, the nodes are far off. Distribution system, the nodes are closer by. You could have a home area network either to control the devices within the house or maybe a few neighborhood houses, field area network to control the locality, a large locality, and wide area control to manage a large geographical area like a state. Though some of us may be having a basic understanding of what type of communication devices should we use. However, for the ease of those who have got a not so clear understanding, we have classified the communication layers based upon the based upon the system for which we have to work. In the case of distribution system, in the case of household system, as you see, we have got devices, example members like thermostats, we've got pool pumps, field tools, personal computers, building automation. These are the type of members that need to be managed. As we go higher up in the distribution system, we typically use a neighborhood area network where we try to interact with one smart meter to the another unit using, we have got different smart meters passing on the information to the data concentrator unit or the aggregator unit. The typical components in at this level could be relays, modems, bridges, access point, etc. These data aggregator points pass on the information to the meter data management system at a level what we call as wide area, using a communication architecture what we call as wide area networks at a level of the transmission systems. Essentially, what we require is routers, towers. What are the essential members are the routers, towers, ground stations, ring mains, repeaters. These are the existing members that exist in the system. At a much higher level, the meter data management system is at the enterprise level. There are a variety of such systems which process the data. They process the system operation and generation and operation data based upon the MDMS data available with them. The type of examples could be, the components could be MDMS, billing could be one of the processes that they do, outage management system, energy management system, so on and so forth. They may be operating those mechanisms. Beyond the enterprise level, there would be external users who will be using it. Those external users could be market players who will be using that information. There could be service providers who could be using that information. There could be individual customers who would be accessing that information over their individual devices, handheld devices, which are not a part and parcel of the grid system as such. In such cases, for such scenarios, some of the example members could be the retailers, aggregators, regulators, customers, and so on. Now, to understand the applications for different communication technologies, we need to, you may have heard of one or more of those. The key thing that we need to understand is when we are designing home area networks, the type of communication architectures that we need to use, communication devices that we need to use, technologies that we need to use, something related around Zigbee, they could be Wi-Fi, they could be LoanWorks, they could be open area network. These are the type of technologies that are typically being used for home area networks, Zigbee and Wi-Fi being some of the most popular ones. For a neighborhood area network, the type of communication technologies used are different. You may use a cellular technology, you may be using old type of ADSL technologies, wireless mesh, BPL, WiMAX. These could be some of the technologies that may be used for a neighborhood area network. While we go in for a wide area network, we may be using satellite communication or any other form of these communication indicated here to transfer the information between different stakeholders. As you still go up at the enterprise level, you could be using communication architectures like IEC 61970 or 61968, or other architectures like web services, etc., to coordinate information between different members using certain technologies. Similarly, for providing information to the external stakeholders, we could be using architectures like www or internet, these architectures to transfer information from the portal to different people, different stakeholders who are using these systems. So the key question, that key change that is happening in the system is ICT getting embedded into the system. It obviously makes the system smarter. However, at the same point of time, it also makes the grid vulnerable. So one has to be wary about what are the points, what are the access points where, while communication is happening between one node and another node, what are the nodes at which an external entity can get access into the system. Why this is happening is because as there are more and more monitoring and measurement devices, as those devices, we need more and more intelligence. We are embedding more and more intelligence into the system. If anybody penetrates into those devices, the local intelligence can be controlled by somebody else rather than the device in itself managing that intelligence. So that is one of the security challenge. Second security challenge arises because of significant network connectivity between different nodes. So communication, wherever communication between different nodes, between different devices through those nodes is happening, it creates an open point where anybody can enter into those communication channels and penetrate and hamper the operation of the devices which are communicating with each other. Another change that is happening is automation in the system. With more and more automation, the decision making is happening in the system itself. So there are closed loop processes which control the capability of system to operate. These changes that are happening in the system, they essentially make the system a cyber physical power system. And these changes in themselves present a security challenge. The changes what we call as that of The intelligence, communication, and automation (ICA) challenges. These represent the comprehensive set of challenges that arise for the power grids. And as these intelligence, communication, and automation is increasing, so is the likelihood, the frequency, as well as the sophistication of penetration into the system, sophistication of cyber threats in the system is increasing. So as you make the systems more automatic, the risk level again increases. As you make the system more connected, the risk level increases. And so also as you make them more measurement, more intelligence you embed into the system, they become more and more vulnerable to cyber threats. Impact of those cyber threats could be significant. It could lead to power outages. It could lead to physical damage to the infrastructure. It could lead to reduced reliability in the system. If there are failures, it could lead to public safety challenges, economic impact on the economy as a whole. Data theft is again a challenge. Personal data about electricity consumption that would be known to public. And eventually it would also lead to a loss of public confidence in the system, thereby hampering the cause of more automation, more smarter grids. So there is always resistance between the stakeholders, specifically the customers, to make the grids more smarter. So are the challenges real or are they merely theoretical? Those challenges are real. Cyber threats, cyber attacks have happened. Cyber physical attacks have happened in past. A large number of those have happened over these years. The frequency and the sophistication of those attacks has increased. The storylines you can see over the last 2 decades, there have been a variety of attacks. Some of those names that you see in 2003, the attack was a slammer bomb penetrated the control system of a nuclear power plant. So essentially a malware got injected and that led to a parameter display off for 5 hours. So that can hamper the operator's ability to operate the power plant. Again, in 2007, there was an Aurora attack in which the circuit breaker of it, so which essentially lies under the classification of false data injection attack. The impact was that the generator exploded. In 2012, if you see, malware affected the RASGAS and Armaco. So this malware injection led to the delivery of energy getting affected in parts of the country for certain period of time. In 2015 in Ukraine, you see attack on breaker settings of few discoms. So that led to that essentially is a false data injection attack, and that led to a blackout. The impact was significantly large. Just taking the case study of Ukraine's case, it was a complex cyber attack which used phishing emails, and malware was embedded into the system that captured the SCADA control, limiting the ability to remove, and limiting the ability of the local control persons to operate the power plant, to operate the distribution system. They were able to remotely switch off the substations. They disabled the IT infrastructure components, UPS, etc. That led to a situation in which the authorized personnel could not operate those substations in an appropriate way. Or add on to that, the files that were stored on the servers, they were destroyed. So essentially, that led to a situation what we call as the services were denied to the stakeholders. Or this comes under the category of denial of service attack, and consumers were not able to get an updated information about the power supply. This type of challenge, this is one of the examples that has come across and that has led to significant impact on the economy of Ukraine. The several distribution system operators got affected, several 100,000 people got affected, large number of cities, loss of power for several hours, damage to devices, and with the climate that was not so conducive, so the people were left in a cold climate to face a situation where there was no sufficient electricity heating in the systems. That those type of attacks can be of challenge to the power plant operators, to the power system operators. So this is just a quick introduction that I have touched upon, looking at the time frame that we have in the class. Any quick questions on what we have discussed till now? We are open to that.
Good afternoon, sir. So no such question, but can we get examples or any hands-on for these two cases, like for demand side management as well as cyber attack or cyber security part, for any case study or any segment?
Use cases, in case of cyber security, use cases may be difficult. The problem with this is, unfortunately, the utilities themselves don't want to highlight their weaknesses. So complete details of recent cyber attacks may be difficult to get. Though theoretical information is available, but I doubt that would be available. How, and on the case of the first part that was on demand response, some of the case studies are publicly available, if not all. The case studies by private those private entities, private electricity suppliers, distribution companies, they may not be available, but some old data, some old demand response strategies would be available. I'll try and share those. Just drop me an email. I'll try and share those.
Yeah, sure, sir.
You want? This is my email address. You can drop me an email at this address. I'll be happy to respond back to you. Any questions other than that? Any questions? Else we will have to close the session. Virendra, Koteshwara, Subrata, Lakshmidhar, Jayant, Jasmine, Gaurav, Ankit. If there are questions you would like to ask on chat box, that also is fine. Please feel free. Okay, then thank you. Thank you all the participants who attended the session. We hope to continue engagement over such sessions and maybe in personal sessions as well. This was an online session. I think there would be a quiz at the end of the program, and I'll encourage you to participate in that to get an appropriate certification. So hope to see you soon. Thank you, everyone. Organizers, we may now close the session.